Okay, so we'll get started as people still streaming in. My name is Sharon Tu. I'm from University of Notre Dame. I'm here to very honored to introduce our speaker today, and is Dr. Gurtej Sandhu. And Dr. Sandhu is a senior fellow and vice president at Micron Technologies. And actually, he is responsible for all the Micron technology roadmap, and he's also trying to find the alignment between all the different departments looking at the emerging technology, what is the next emerging technology, especially in terms of memory related. And Dr. Sandhu received a degree from electrical engineering at the Indian Institute of Technology in New Delhi, and PhD in physics at University of North Carolina, Chapel Hill. Physics is hard. Anyway, I think he has really interesting, I have a really interesting trivia for you guys. Do you know how many patents he has? It's right here, right? How does that compare to Thomas Edison? More or less? More, exactly. So we're just so proud to have Dr. Sandhu today to tell us about the memory future. We all know how important memory is in our lives, so let's hear Dr. Sandhu. He is here, I promise.
Okay. All right, thank you. Sorry, thank you. I don't know, is this on yet? Okay, can you hear me? All right. So the topic for this afternoon is the memory futures. And the picture represents all of your career in high-tech industry. And what it means is that the speed at which this industry moves is out of your control. It's just like going down a zip line. And then you're trying to head in the right direction and hopefully move it in the right direction. So I will briefly go over some historical pieces, but quickly go into what's coming down the future. You all have these devices, and you all know Moore's law, and you all know how powerful the technology progress has been in the last few decades. It's been 1 million times improvement in cost or transistor size, as well as 10 to the 5 times improvement in power. There is no other industry in the history which has actually been able to achieve this. It's very unique to our industry. And what that means is that the computer I saw when I was in college, and with the device you have in your pocket, is 200 times more powerful than the mainframe computer I saw when I was in college. But that's only half the story. The $20 you pay for your memory on your device would have cost $14 million at the time. So it's not just the technology itself or the performance, it's the affordability of the technology. That's what's made it so pervasive all around the world. And that's what made this industry grow. And our lifestyle today depends on this technology. You can't imagine life without any of these gadgets. The question is, what's next? Can we sustain it? So if you look at the solid-state drive today, you have NAND flash chips, DRAM, or 3D SXP chips, or ASIC, which is a controller. Between NAND and DRAM is the most dominant form of memory in the industry today. So it's more than 90% of the market. And the NAND flash typically in your device, which you'll see, is already a 3D device. So we are past the 2D or planar devices, which we all used to talk about in the last few decades. All memory produced today, all mainstream memory produced today is NAND 3D, and it's already on the generation 2 or 3, which goes into your devices, and then there is more generations coming down the pike. And the other chip you see is a DRAM, which is a planar device, but also technically it's also a 3D device in the sense that all the capacitor and the transistor we have been using for many years are all actually 3-dimensional. So there is no planar in memory anymore. It's all 3D. And that's also true for the crosspoint. The starting first generation was 3D crosspoint and going into multiple stacks. So everything has transitioned to 3D. So in some ways, you can argue we are past the planar chips. Now, in terms of the DRAM capacitor scaling, there have been huge challenges over the last few decades. But the point I wanted to make was that the capacitor went into 3D in the mid-90s, and the transistor went into 3D in about year 2000. So memories have been doing 3D devices, although not FinFET, but the U-shaped device, for more than a few decades now. And also this capacitor was also used for the high-K material, which are exotic materials which have high dielectric constant, and that also happened a couple of decades ago. So in some ways, not to try to, I guess, sound like I'm crowing about it, but in terms of new three-dimensional devices as well as new materials, memory actually proceeded to use it by 5 to 10 years before logic did, and that is the fact. And one of the stories of the flash memory is pretty interesting. So this is where the flash cell was invented in the 80s. Then there was a question about NOR flash or NAND flash. That controversy went for a couple of decades. A lot of people bet on NOR flash. Then something happened in the early 2000s. That was Steve Jobs went back to Apple, and he wanted to make an iPhone or an iPod. And he then was looking for a low-cost memory to replace disk drive. And that's where the compromise between the performance and the cost happened. And that's what made NAND flash happen. So within 2 or 3 years of the tide turned, and everybody had to really jump into the flash wagon. And that was true for Micron also. We were doing that NOR, we stopped doing NOR, then we said, we gotta do NAND now because this ship is coming. Now, one of the fundamental mechanisms in NAND is tunneling of electron through the tunnel oxide. And one of the challenges which was never solved was how to scale the tunnel oxide thickness. So we stopped at 70 angstroms, and we never figured out how to go beyond that. What that meant was that you had to use 25 volts to program this cell. What that meant was the planar scaling ended at 20 nanometer because your electric fields were higher at those scales, beyond those scales, than the breakdown field of any materials such as silicon oxide or silicon nitride. So if you look at the transition, about 2005 or 6 is when the Apple phenomena happened, and everybody was trying to make devices. And Micron happened to skip some nodes. We went from straight into 34 nanometer, 25 nanometer, and 20 nanometer nodes. So we had 3 nodes, and the memory was, and the market was growing exponentially. And we knew after 20 nanometer, based on the fundamental physics, it would not scale anymore. What do you do now? You have a huge memory market, you just started, and it was also taking off in the server space, which was a little bit unexpected. So the question was, how do we get around these technical problems, which are physics driven, which means the engineering is hard to, sometimes it's harder to engineer out problems which are fundamental. Well, the solution was to go 3D. And after 3 generations, we went to 3D, and rest is, as I've said, you can see these devices in your pockets today. So the question is, what happens now? So, well, with 3D, we are still limited by similar situation as before, the economics. If we keep gaining offering lower cost, better form factor, a better value to the customer, it'll still keep scaling. And you have to you have to work on some engineering issues, such as defects and yields, as well as some structural problems. So both DRAM and NAND, in a way, are what I used to like to call MEMS-type devices, except these are MEMS devices at nanometer scales. They have an extreme 3D, third dimensional, a few microns, and in the other dimension, they're nanometer-sized devices. So it's a pretty unique problem from both device as well as structural issues. Now, NAND also has been able to do multi-bit per cell. And when people talk about MLC or TLC, which is 3 bits per cell, and so recently we announced QLC, which is 4 bits per cell, Micron was the first ones to announce. Just imagine the technology challenges. Each cell has to distinguish between 2 to the power 4 16 states. Each cell has to maintain those 16 states. You have to be able to distinguish which of those 16 states is programmed in the cell. And you have to do it over trillions of devices on a wafer. It's a pretty amazing feat of engineering which our industry has been able to achieve. And this has happened through collaboration between the process, devices, and this design. It's been a complete collaboration and at the system level. It's a pretty amazing feat of engineering that you can do this type of precision. So overall, memory has been driven by creative solutions to surmount very tough technical challenges, as I said. Most of our devices went 3D a long time ago. We had to introduce a lot of new materials, and then we had to keep finding a way to scale down the path of Moore's law. But Moore's law is slowing, everybody knows that, and for NAND, it ended a few years ago. So Moore's law is history for NAND. That's why I went to 3D. And the question is what happens for DRAM and other technologies. So while all this is going on, when I joined this industry and at Micron, we were hoping for a killer app, which will really increase the demand for DRAM. And that happened with the first personal computer. Dell computers introduced a personal computer. Everybody was supposed to have one. That was the first killer app, and the DRAM industry took off. For 1 year, we made a lot of profit. We didn't know what to do with it. And then it tanked again because everybody got involved. So the problem with lack of diversification always is the economic issue. Now from a one killer app, we are down to two major mobile and enterprise, as well as there's all these other fields which are coming up right now. Automotive is huge, and there's all kinds of different fields. So diversification is taking place, which is increasing the stability of this market. And there's a slide I saw from somebody a few years ago, and what this slide shows is a vertical scale is percent of devices, and the horizontal scale is the year. These are percent of memory devices built by all companies, all wafers produced in all factories in the world. So if it's a logic device, Intel logic device, maybe 50 to 60% is SRAM cell, so you count that as 60%. DRAM is mostly 80+ % is memory, and NAND is really large memory cells. So these are devices built. And first I looked at it, it was pretty interesting. So then we did a conservative approach. So that 30%, the low number is our conservative approach, and the high number is actually by a third party. So according to this, in 2015, either 90 or 99.99% of the devices built by all companies across the globe were memory devices. It's kind of hard to think about it, but that's the number you come up with. And that was 3 years ago. So now it's an argument of is it 99 point, how many nines? Is the number of devices which are memory as opposed to logic built by all companies in all factories every year. So that's how much memory is pervasive in terms of our everyday life and everything we do. And the NAND clearly drives that. The number of devices is so much, it's skewing the whole market out to, it's taking off. That's what it means. So in general, for the memory, while we are having these technical challenges, but the applications, as I mentioned before, are all over the place. So some of the big applications are in the compute and networking, which are historically has been very robust, embedded and storage, and the mobile. Those are the big markets, and there's many more coming up right now. So if you look into an average, let's talk about autonomous driving, which is more real than we think, because you can see cars which can almost attempt to drive, self-drive. They don't do a good job of it, but they're getting better really fast. So in a typical system architecture problem for these devices, memory really impacts majority of the modules. And memory is extremely important to enable the design of these to the optimum performance. Of course, you need to have a fast CPU for sure, but you got to feed a lot of data into the CPU to do anything on a real-time basis. So what's the future? So in general, if you look at different markets, there's an exponential growth of data projected. So you look at astronomy, which represents the scientific computing field, could be weather patterning and space travel, anything. YouTube is the consumer side of things. In the next 10 years, they're expecting an exponential increase in demand for these memories. But then there's a new field of genomics, which is essentially using the DNA mapping and looking at the correlation of data over a longer time and using it to do better healthcare and maybe create better solutions for medicine. The projections there are so huge that the scale breaks. And the amount of data which they expect is needed will dominate any other industry. Now, why is that? No, we like to call it medicine meets big data. In terms of the human genome, the DNA can be mapped. You can all afford to map your DNA. It takes a few $100s. Once all the data is going into the database, and each unit of information is about 5 terabytes. So that's a lot of information per person. And once you find correlations, you can use it for better healthcare. But this is only part of the story. What we really need to know is what's going on with our microbiome. We all have these microbes inside of our body. For example, in your gut, the microbes help you digest food. There's many other types of microbes in your body which live in a symbiotic relationship with you. And they are very important for your health. There have been some recent studies which say there's changes in the DNA on the microbiome which happen 1 year before people get sick. So imagine people hardly go to the doctor now till it's really a problem. Imagine a year before you're even going to get sick, there'll be some markers. And there's something can be done about your health. So, and that information, since it's a different types of microbiome, it's very rich in DNA information. It's 10x more richer than the 5 terabytes I showed. So this is potentially going to drive a lot of data requirement in this. And the reason it's going to happen most likely is because healthcare is very important to us. We all like to live better. But also healthcare cost is a big deal. So if you do preventive care using these type of technologies, you can make some changes into and find some changes in the lifestyle long before you get sick, and the cost of the healthcare is much lower. So, and everybody's heard of AI, which is certainly going to touch every part of your life, whether it's the mobile devices who can recognize you, which is already happening, or they can actually listen to you, which is already happening with Alexa and Google in your houses. It's going to be a lot more pervasive. Autonomous driving, as I said, is coming faster than we think. And all this is going to drive a lot of memory requirement for both AI training as well as for implementation in the field. And the thing about training is that these AI modules will be training all the time. So every 6 months, they'll have a better trained AI downloaded to your device. But in the background, the more data you have, better training it gets. So there's a huge demand which will be required, both for training it as well as in the remote locations as well as on your device. So in all of this, one thing we do need to consider is one of the biggest challenges we have at the system level is feeding the data into the processor from the memory. And that's it's been called a memory wall or a barrier. And there have been a lot of innovative solutions over the years. We're doing much and much better now. However, physically, it's a bottleneck. We have actually researched into photonics and any technology we can think of out there. None of them are practical. So the question really is that how can you get 10x to 100x improvement in this data barrier or the memory wall between processor? So one of the concepts, this is not a new concept, it's been an old concept, is to move some of the processing into memory. Why move lots of data to do a little bit of processing? You can move the processing into the memory, do the processing where the data resides. And that's one of the things in the future we'll have to do to get around this issue. It's not optimal for all problems, but some of the problems, it may be the best way to approach that problem. So these chips can be built. Many companies in the past have built these chips. Micron has built these chips. The barrier is not the chips. We can build those. And we have shown 10x to 100x improvement in power and bandwidth. The challenge is to write software and the firmware from scratch. You have to start all the way at the beginning, because everything written today assumes a certain architecture. And maybe IoT is a space where you have to rewrite, start from scratch. Maybe that's where we can implement some of these technologies, because you do need to have solutions which are low power as well as a compact in form factor. So in terms of memory roadmap, hopefully I've convinced you that the Moore's law, as represented by the dotted lines here, is slowing down, because the vertical is the cost per bit, and the reduction in cost per bit with time is slowing down a little bit. And for the green curve, the transition you see is the 3D. Going to 3D, it slowed down a little bit, but once we are on 3D, we are still in a good pace. Maybe not same as before, but we'll see how far we can sustain that. And the DRAM is slowing down also because of the complexity of cost. And so, however, our industries are always innovative. So as I mentioned, we can go into the 3D. NAND has gone to 3D. For DRAM, we're already doing stacked DRAM chips. Hybrid memory cube is really improving the form factor and as well as the bandwidth. Then we have developed some new storage class memories, which I'll talk a little bit about in the next few slides, which also helps address some of these system-level performance challenges. So emerging memory, why look for a new type of memory other than DRAM and NAND? So about 10 plus years ago, I initiated this program within Micron and asked my customers, what do you want? Internal customers, what do you want? They said, build a memory which is better than NAND and DRAM. Have a universal memory which can outdo everything, so we can just dominate after that. Okay. Usually, I'm a physicist and a double E by training, so every time I face a tough engineering issue, I go back to physics. Because you look for answers in physics, what's fundamentally possible. And that's the best an engineer can do within the bounds of physics. So don't try to beat physics usually with the clever engineering, because no amount of clever engineering can beat physics. So after 1 year, my answer was, there is nothing which can fundamentally do NAND and DRAM be better than that. And I'll show my example in the next slide. So then I said, what do you want then? Well, how about beat DRAM in its own space and NAND in its own space? So let's have a better memory. So I spent another year on this, and my answer was, no, can't be done. And I'll give you an answer in the next couple of slides. So you went back to the simplest model of, physics model of a memory. You're moving charge from point A to point B, and absence of charge or presence of charge in point B is a 1 or a 0. And the control system is a transistor, which helps you select that cell. So if you write a simple physics equation, the simplest equation, which assumes perfect materials, perfect engineering, this is the best you can ever do of an electron tunneling through a barrier. You come up with these simple numbers. Every memory type, which is storage-based, fits that table. DRAM is about half the band gap of silicon, about a few milliseconds of retention time. Flash is 1 plus EVs. The retention time can be a year to 10 years. So fundamentally, every memory type we have follows this equation. So here's the problem with that. When you have a high barrier, you will have retention. For retention, you need high barrier. However, your tunneling probability is very slow. So it's going to take longer. The memory will be slow. So either you can have a slow memory, which can have retention, or you can have a very fast memory like DRAM, which will have very little retention. This is what you get. You can't go beyond this. This is the fundamentals of the physics which control. So our answer was, okay, let's look at alternate storage mechanism. You cannot store information in the form of charge. How about different mechanisms? Moving atoms, phase of a material where atoms have to displace from point A to point B, which could be ferroelectric. All these memories you hear about are that class. Or look at moving spins. You don't move the charge, but spin. So that's the STRAM and racetrack memory. So when we started looking at it, Google was new at the time, and we were very proud that we can search using Google. Every week, there was multiple new memory types claimed. And what usually used to happen was that researchers will try to make a device, transistor. When it only worked once, they'll call it a memory and publish. Okay, this is a memory device. So the problem we had was, okay, how do we select what works, what's not? And then we went back to the physics again. Let's look at the fundamentals of what drives these devices, and what can those fundamentals do relative to the fundamental physics of NAND and DRAM. And that's where we categorize this based on that. So along the way, we started to think, so let me go back to my other answer, that why DRAM and NAND cannot be replaced. So NAND is a 2-in-1 cell. There is no select device. Select device and a memory device are all in one device. So that's a 2-in-1 cell, I call. So because you have to be able to route your signal, select the memory cell, and then store information in it. Usually takes 2 devices. NAND does it with 1 device. Now that's pretty hard to beat. Now to make things worse, NAND can store more than 1 bit. And I show you there's a 16 levels now we can store, so which is mean 3 bits or even 4 bits. Try to imagine designing a new cell which can beat that. Pretty hard. On the DRAM side, nobody really knows, is there a limit to endurance of DRAM? So I was trying to build a device to say, okay, give me a spec for endurance. What endurance do you need? And our customers will say, well, same as DRAM. No, I need a number. No, same as DRAM. So, well, we can't measure it because it never fails. You got to give me an expectation. So, no, same as DRAM. That's the answer. So the best numbers we have come across based on the system level calculation of when the systems can fail, will fail eventually, or since systems don't fail, is 10 to the 22 cycles. Imagine trying to come up with a new memory which can do 10 to the 22 cycles now and still have the same power envelope. So all those are technical issues. Even a bigger issue is the cost issue. You have to beat those technologies at cost and perform the same way. So our answer was that all these technologies can be better or match those existing technologies in some parameters, but they can't really match the data sheet. There's no way to match the entire data sheet. So you have to find new use for these memory types and see what the benefit is going to be. And fortunately, by that time, NAND had already taught us a lesson. NAND came, as I said, for phones, and we were pretty happy about it. We used to wish that one day we will maybe take up some space from the hard disk drives. So what happened is those guys looked at the system level, reliability issues, cost issues, and so forth. They found out that SSDs could actually help them at the system level, even though the cost per bit was higher, 4x higher in some cases 20 times higher cost per bit. It still made sense to use it. To this date, NAND has not beat the hard disk drive on cost per bit, but overall system cost and performance because of the latency, which is in the milliseconds, which is in the microseconds as opposed to milliseconds. So you always have to be looking at now memory types and implementation at the system level and see what fits. So that gave us a new way to look at these technologies, and that's how the 3D crosspoint technology was introduced. It was positioned to fill that space between NAND and DRAM in the memory hierarchy. So it's faster than NAND, slower than DRAM, much lower cost than DRAM, but higher cost than NAND, and so forth. And that's how you position these memories, and that's what the benefit is. So I guess this is 1000x faster, much higher endurance than NAND, and denser than conventional memory. So, and that potentially enables new types of memories, new types of applications which you can't do otherwise. And that is the hope here, that with these new technologies, you offer a value to the customer, both in terms of cost and performance, to do a function. So you have to go and look at it at a much higher level. So in terms of, and this is the first memory to be introduced in a big scale in this way in the last 30 years. We have researched many memories. Micron actually published 16 gigabit CB RAM at VLSI almost 7-8 years ago. We built a chip. It worked. It had a data sheet. There was no takers, no application for it. So that's when we figured we need to be starting from top down. So where in the architecture can we offer a solution? What does that solution need so we can service that market? Anybody needs a 16 gigabit CB RAM, we have it. It functions. Let us know. But it does not meet it has its own data sheet. It does not meet data sheet of anything else. Just like NAND does not meet data sheet of anything, 3D crosspoint doesn't meet data sheet of anything. People actually forget, the same people who tell us, give us DRAM again, forget DRAM came about only because Intel wanted to have something lower cost than SRAM. DRAM was invented in IBM and ignored for a few years. Intel was making SRAMs, and they knew that their future of processors depended on a fast, low-cost memory. So they enabled DRAM. The service DRAM, every bit on a DRAM is refreshed every few milliseconds by a processor. That's a lot of heavy lifting done at the system architecture level to enable DRAM. Nobody, can you imagine a DRAM working otherwise? So all this memory technologies to this date have always been top-down. Never once was there anything bottoms up. That is my conclusion out of this. So any new technology will have to be thought of top-down, which is this audience has to be thinking of where is an application, what's the data sheet you need, then we will figure out how to match that data sheet. And the cost. It has to be both cost and performance. So in terms of materials, I alluded to earlier, so of course the conventional, in the 80s, chips used to use few metals. And just to add copper into the industry for logic and eventually for memory, it took us 10 years of conferences to think about copper, what are we going to do about copper, can we handle it, and so forth. Once copper was done, the next few materials came in at a rapid pace. So right now, we use a lot of these are in manufacturing. But in the research stage, we pretty much haven't left anything out in the periodic table. The only thing which is left is either there are gases, so we don't know how to make a device out of what's usually a gas, or they're radioactive. So my prediction is gases, maybe we don't know what to do unless we go to space. We won't be able to find a use. But for radioactive, yeah, we'll find a way out. Maybe if it's a very long half-life, manage the radiation, put a little lead around it or something, we'll find a way. So that's our hope, that we keep looking for these solutions in terms of the materials innovations. So for anybody who's doing material research, it's a great time to be materials research because we are looking at everything on the periodic table. However, there's a big but. Just looking at new materials to make conventional devices in a conventional way, just scanning through materials and hoping something works, those days are over. All the big companies have invested a lot into this research. If you could make an existing device better, just coming up with a new concoction of a material, there's a very low opportunity there. What you really be going after is looking for new physics and new mechanisms with these materials. So for example, the 2D materials, these graphenes or any of the other 2D materials, those are new mechanisms and new physics. And some of these materials are predicted from physics and built later. So we have extreme ability in modeling these materials. And at this conference, you see some of that we have an amazing capability now to model materials and predict those materials. And it has happened more than once now in the last 10 years, where somebody theoretically predicted a new material. Then somebody went and built it, and it turned out to be exactly how they predicted it. That's a huge opportunity, because any new mechanisms or any new devices we can build will have unexpected new applications. As I said, physics always is important. New physics using these new materials is extremely important. So in general, hopefully you're convinced that the memory market is undergoing expansion and the application space is getting a lot more diverse than it used to be in the past. And it's rapidly increasing. It's not a linear curve, it's an exponential increase. And the march towards 3D is likely to accelerate. Pretty much everything we do is 3D now. Once again, logic is planar, but we are 3D. But logic will go there too eventually, hopefully. Each market application is going to have different requirements. So we have to really have an application or a market-based assessment of how to utilize this technology. The days of bottoms-up innovation are over for these devices. In my view, they never happened, even if you look at the DRAM. It's just a misnomer in our minds that the bottoms-up innovation is what happened. So the collaboration between different companies and a different part of the food chain is extremely important. NAND would not have happened without Steve Jobs and Apple. And all the new future technologies the same way. Look at the application, look at what's needed, what makes sense, and develop a new technology. And the value proposition is really, as I said before, is at the system level. That's where you start. And there's huge opportunities to research new scalable memory systems, which can actually enable a lot of new memory applications. And it just needs to be a different type of innovation than what we have done before. Either new physics, new mechanisms, or looking at the architecture level and finding those solutions. IoT offers so many new opportunities. AI offers a lot of new opportunities, by the way. So far we have brute forced the AI, but the future of AI, there could be many new different type of devices which will be very efficient at enabling AI. And I think that is my, thank you. Thank you for your attention.